Thank you everyone for being here today for our Friday noon seminar. Today we have the great pleasure of welcoming Dr. Dan Ma. She is an assistant professor in the Department of Biomedical Engineering at Case Western Reserve University in Cleveland. Her research focuses on the development and clinical translation of innovative quantitative MRI technology, and she is the key inventor of MR fingerprinting and the first author of a seminal paper on this topic published in Nature, which you don't often see in medical physics, so that's very interesting. Dr. Ma has also made significant contributions in making quantitative MR fingerprinting fast and robust for various clinical applications. So with that, I'll let her explain to us more about what is MR fingerprinting. So please go ahead.
Thank you, Dr. Wilson and McGill Medical Physics Unit for the invitation. It's really my pleasure to present this, my research. So my background is on MR physics and engineering. My work focuses on MR sequence design and reconstruction and then clinical translation. So today I'm going to talk about a quantitative MR scan called MR fingerprinting. So I want to first of all talk about qualitative and quantitative. What's the difference between qualitative and quantitative measurements? So this is a very simple example that when a kid doesn't feel good, so the very fast and direct way to tell whether she has a fever or not is to touch her forehead. So it's basically a feeling whether her forehead is warm or cold, but it's a very qualitative measurements, and it's really hard to communicate with other people or to pediatricians unless you have a temperature measurement. So here, 103 or 39 degrees basically indicated that she had a fever. So this is the difference between qualitative measurement and quantitative measurements in a more of a general term. So back to the MR, most of the clinical MR, we call it contrast-weighted images, such as T1 weighted or T2 weighted images. Those are qualitative measurements, I want to say, because the intensity of this MR images does not mean anything. It's basically a relative, this image shows relative contrast between tissues, among tissues. So as we can see, this patient case, you can see that there is a lesion that looks brighter as compared to the surrounding tissue types. So radiologists may say it's hyper-intense or hypo-intense compared to surrounding tissues. But this is more of a qualitative description of the contrast. That's the bright mean lesion not necessary, because once you change the scan settings, the bright can go dark. Does the brightness corresponding to severity of the disease? Also not necessarily, because again, once you change the scan settings, the brightness may change. So it is really a big challenge for reproducible or standardization point of view that this image contrast can be different depending on the measurement settings, heavily depend on measurement settings. So once you change the acquisition settings or switch to different scanners, different size, or even different days, the image contrast can be different. So here's one example. We call it MRI T1 weighted images from 3 different vendors. Do you see my mouse, or yes or no? Okay. So
Yeah.
So different rows shows the T1 weighted image from different vendors, 3 different vendors, and you can clearly see that the image contrasts are different across vendors. Those differences does not mean that this subject has a lesion or not. It's just a natural different scan settings. So what variations are we measuring if we have such high variations from the measurement already? So here is a diagram showing, the height of this bar basically illustrate the variation we might get from different sources. So we have this measurement variations that we already see the intensity difference. And then we got biological or physiological variations from subjects, such as age, different populations, or across different sites. And the pathological variations, for example, lesions or brain tumors, epilepsy lesions, and other things. So if our end goal is to identify pathological lesions, but we also have variations from measurements or physiological variations, it's really hard to piece apart those sources of variance. So that's why when people are doing multi-site data analysis, the first step is to harmonize those data. But still, what variation are we measuring is really hard to answer, given that there are large variation from all three different sources. So if we look at the pipeline, starting from MR image generation to the downstream image analysis and to the clinical translation or clinical support, we already have large variation from the first step where we generate those images. And then we can imagine that those measurement variations will go to the image analysis step and may also affect the last step, which is the clinical decision support. So the goal is really how do we change the pipeline from the starting point or the image generation side. So this goes to the point that I want to bring is to change the qualitative MR measurement to quantitative MR measurement. So what's the difference then? So here's one example. Still clinical MR T1 weighted image from epilepsy patient who has periventricular nodules. Sorry. So here are the lesions around the ventricles, a giant lesion, and all these dots, the blue dots, can be the size of the seizure onset. But from the clinical MR T1 weighted image, it's really hard to tell which side caused the seizure. So as a result, there has to be some more of an invasive measurement to detect the seizure. So this is a typical detection measurement called SEEG, where they basically implant those electrodes, multiple electrodes into the brain to those regions in order to detect the seizure, and in that way to identify where the seizure from. So you can see it's quite invasive diagnosis tool. It's not even a treatment tool. So on the same patients, we did some the MR fingerprinting, which is quantitative MR. So here we show a quantitative T1 map. So here is T1 weighted, and here we basically measure the T1 relaxation time. So you can see the color bar, the number shows here is in the unit of milliseconds, meaning that the difference, of course, we use different color to show the difference, but the true difference is that in the quantitative T1 map for each pixel, it shows absolute value of T1 relaxation time. So it's quantitative measurements. And one thing is quantitative. Another thing is that we can clearly see that, okay, this area has high T1 as compared to the neighboring lesion, where we don't see much clearly from this MR T1 weighted image. So in fact, this patient had this invasive SEEG, and we got some validations that this region corresponding to high T1 value is actually the actual seizure onset, meaning that the increased T1 value from this actually means something that's related to the seizure. So yeah, this patient after he got the ablation to remove the lesion and become seizure free. So as a pretty short summary is that the difference between qualitative and quantitative, one thing is that quantitative T1 map provides numbers. So you can draw a region of interest, measure the difference in T1, where we can say that, okay, the lesion that caused seizure will have increased T1 of 8% as compared to the lesion which has no seizure outcome. And also, this is the more sensitive measurements as compared to the clinical MR. So as I pointed out, there are some benefits of quantitative MR technology, but in clinical MR, we don't see any quantitative measurements at all. So the main reason is that it takes a long scan time, so it's not efficient. So lots of quantitative maps or scans are not being used in clinical setting. So the goal of MR fingerprinting is to really develop a fast, robust, and multi-parametric quantitative MR technology. Fast meaning that we want to develop a scan that can be used in clinical settings, and robust meaning that this scan can be implemented in different scanners, maybe quantify tissue properties across the body. Multi-parametric is also another way of improving scan efficiency. So when we talk about T1 weighted or T1 map or T2 map or diffusion map, all these are quantitative maps. Can we use just one scan to simultaneously quantify those tissue maps? Then we don't need to do scans one by one. So this is the basic idea of the Nature paper we published 10 years ago. Yeah, so why we call MR fingerprinting is because the basic underlying concept is similar to the actual fingerprinting technology. That once you have a fingerprint, it doesn't matter how this fingerprints look like. If you have a comprehensive database, you can use some matching technology to find these fingerprints from the database. And once this fingerprints is identified, a whole list of information related to that person can be extracted simultaneously. We don't need to find the name first and then phone number next. Everything is stored that is linked to the unique fingerprint. Similar idea for MR fingerprinting. So we first acquire a series of images with totally different contrast. From each pixel of this image, we can plot a signal evolution curve. And it doesn't matter what the signal evolution curve look like. We can build a comprehensive database that stores the signal evolution curves that is governed by multiple tissue types. And then we use some matching technology to identify this curve from the database. And once this curve is identified, the underlying tissue properties, similar to a person's identification, can be extracted simultaneously. So in this example, we can quantify quantitative T1 map, quantitative T2 map, proton density map, as well as system performance simultaneously from a single scan. So this is the basic concept of MR fingerprinting. So after the first initial implementation, we collaborate with Siemens to really translate this technology to a product. So this was the original 2D MR fingerprinting scan. So already clinically feasible, 20 seconds resolution 1 by 1. And so after the scan, the quantitative T1 and T2 maps will be generated on the scanner. So my lab has been working on developing more robust and whole brain coverage scan. So this is a 3D whole brain MR fingerprinting scan with 1 millimeter isotropic image resolution. So after the scan, T1, T2, and proton density map simultaneously quantified without additional scan. So from the same scan, from the same data, we can also do the following image analysis. So for example, this is the tissue fraction maps. So this is also a quantitative scan result because we can estimate for each voxel what's the tissue fraction of gray matter, white matter, CSF. So so everything from this slide are quantified simultaneously from a single scan. So one thing is that it can be very time efficient. Another thing is that because all the results are from the same scan, those maps are inherently co-registered. So we don't need to do the follow-up image registration across different contrasts. It's just the same co-registered images. So in order to fully integrate the scan to the clinical workflow, we also collaborate with Microsoft Quantum team to really optimize the MR scan so that it can be more accurate, more robust, and fast. So this is as a result of this collaboration, we were able to reduce the MR fingerprinting scan of the whole brain to only 5 minutes with 1 millimeter isotropic image resolution. So why do we care clinically though? So we already have good looking T1 weighted images, T2 weighted images, and have been widely used for diagnosis. So if you look at the conventional MR protocol, clinical protocols, it's typically about 30 minutes with T1 weighted, one scan followed by T2 weighted FLAIR, which is the fluid saturated T2 weighted scan. So one scan after one scan, each one generate one contrast. So for MR fingerprinting scan, as I mentioned, is one single scan, 5 minutes, create tissue property maps. So this tissue property maps include T1 relaxation time, T2 relaxation time, proton density. And we later also incorporate diffusion scan there, which generates apparent diffusion coefficient, fractional anisotropy, everything from a single scan. I've already showed that using the same data, we can perform segmentation, such as gray matter, white matter, CSF. Another important feature that we can get from the MR fingerprinting scan or from the tissue map is that we can use this fundamental tissue map to synthesize clinical images. So that includes T1 weighted, T2 weighted images, because we know the T1 and T2, we can use existing model to synthesize T1 weighted, T2 weighted images without adding scan time. That includes all sorts of synthetic MR contrast generation as well. So everything can be derived from this 5-minute scan. So this is one example, again, epilepsy patients with focal cortical dysplasia. So this is the very challenging case with transmental sign. So here, there's no sign from the clinical T1 3T. We cannot detect anything. We call it negative MR. But this patient had 5 negative MR over 10 years. So meaning that this patient kept having seizure, and there's no way from the clinical MR they can find the lesion. But in fact, there is a lesion here, which is a very subtle tell, can only be seen from 70. So this patient had MR fingerprinting scan. So as I mentioned, direct outcome for the MR fingerprinting is the T1 and T2 maps. So directly from the T1, T2 maps, we can see the subtle lesion here already, showing that the improved sensitivity from the quantitative maps as compared to clinical T1 weighted image. Synthetic MR, we can use the T1 map to synthesize T1 weighted images that matches the contrast with the clinical MR, same as T2 weighted. So now using this from the synthetic MR, we start to see the lesion where we don't see from the actual T1 weighted image. So also the capability of synthetic MR is not limited to clinical MR images, right? We can also synthesize any new contrast that enhance the image contrast. So for example, I can use the T1, T2 maps to synthesize, this is another new contrast that basically enhance the cortical regions now. So I can saturate the white matter region so that the lesion is further highlighted. This is another new contrast that we can synthesize retrospectively. It's called edge, where I can numb all the boundaries while highlighting this lesion. So there's an infinite number of images we can synthesize using the baseline T1, T2 images without adding additional scan time. And the last, and there's also segmentation where you can see this lesion pretty clearly as we basically enhance the contrast among the boundaries. So everything is from the same scan. As I demonstrate, you can use this scan for synthetic MR with commonly seen MR contrast and not commonly seen clinical contrast without adding scan time. It's really provide a lot of flexibility in terms of imaging. So in terms of flexibility, I also want to say that MR fingerprinting is a very general framework. Basically, because there's, like the fingerprints, the human fingerprints, there's no requirement of the shape of the fingerprints, right? Everyone's fingerprints can be arbitrary shape. So for MR fingerprinting, the detect signal can be arbitrary shapes as well. That gives us a very high flexibility in designing MR sequence. So for example, we can randomly change the number of RF radio frequency excitation pulse. We can randomly spacing them or different flip angle values. We can randomly change the gradient area or timings, different acquisition parameters. So all things can be arbitrarily changed during the sequence design. So it's basically a good framework to explore all degrees of freedom in sequence parameter design. So I want to show you some examples. So for example, I've showed the MR fingerprinting scan that is able to simultaneously quantify T1 and T2 relaxation times. There are also other MR fingerprinting versions that quantify other tissue parameters. For example, on the left, I show the MR vasculature fingerprinting. Well, using the same framework, but different designs, they were able to quantify some perfusion-related tissue properties, such as cerebral blood volume, vessel radius, oxygen saturation level, and so on. This is the new research from my group that in addition to relaxation or T1, T2 relaxation times, we can also quantify mean diffusivity, FA and color FA from the same scan as well. So basically, we can basically incorporate different modules to quantify different number of tissue properties from a same scan. So because everything is from the same scan, images are co-registered, no distortion from diffusion. Is quite convenient for image analysis. When I mentioned robustness, we've also used this MR fingerprinting scans across different fields. So this are from other group study that they've already implemented MR fingerprinting to from 0.55T to 7T. It's quite robust across field strengths. I also want to point out that for the ultra high field, one of the main challenge for MR design on the ultra high field is that the field inhomogeneity is much severe as compared to the clinical 3T scanner. Because of this very high flexibility in MR fingerprinting scan, we can quantify the field inhomogeneities the same time as we quantify T1 and T2 maps. The benefit is that the resulting T1, T2 maps will be less affected by the field inhomogeneities. So this is also applies to other confounding factors, for example, B0 inhomogeneity, which is the main static field inhomogeneity. So here is one example from my colleague working on body imaging, where when you scan body, there's much severe B0 and B1 inhomogeneities that they have to deal with. So by quantifying tissue property at the same time as those field inhomogeneities, one benefit is that the resulting T1, T2 maps are less affected by this inhomogeneity, which means that the results are more accurate and probably more reproducible across sites. And also the field inhomogeneity mapping, those maps are subject dependent, meaning that it provide more accurate information while you want to when you try to correct those tissue property maps. So again, this is another I've already showed the 7T, but it's a similar concept is that if your model already accounts for field inhomogeneities, the resulting tissue property maps can be more accurate and more reproducible across different fields. So after the initial development in the neural, there are also other groups and the institutes start to develop their own MR fingerprinting versions and that were used for cardiac imaging, liver, breast, and the hip. It's basically, I want to emphasize that now the images will have the color bar showing the numbers now, and also it's quite robust across the body. This is the main difference between quantitative MR fingerprinting versus the clinical MR now. So I mentioned that one benefit is that one comprehensive scan. Once we have numbers, what's other benefits we can use? What can we use those numbers? One is that we could use this numbers as a quantitative marker. Now we have numbers, maybe we can decide, okay, how bad of the disease. And also, as I mentioned, when we quantify tissue properties at the same time as other confounding factors, the resulting numbers can be more reproducible. So there's a big opportunities for multisite. So as I mentioned, this example is actually, we can actually use the T1 relaxation time as an indicator of the lesion with seizure onset. So of course that requires more patient studies, but now we have numbers. Maybe we can use those numbers to show that, okay, this lesion may be more, how to say, is epileptogenic rather than non-epileptogenic. So this is the one example. When we use the MR fingerprinting scans to scan more patients with periventricular nodule cases, and we've identified this consistently high T1 value from the seizure onset zone versus non-seizure onset zone. I want to emphasize that both zones show as lesion, but some part of the lesion may cause seizure, and other parts may not. So using this quantitative markers, maybe we can identify what's the which lesion is a seizure onset zone versus non-seizure onset zone. Another uses of those quantitative markers is for treatment assessment. This is a new study that I participated in, as to evaluate the treatment response for breast cancer patients. So for breast cancer patients, they typically have the chemotherapy before the surgery, and with the hopes that the chemotherapy will reduce the lesion. But this process can take 4 to 6 months, and many of the patients have to go through this chemotherapy, the entire phase of the chemotherapy. The result from the chemotherapy is not that fully responsive. I want to emphasize that this number is it's pretty sad to see that non-response is 24%, partial response 54%, and total response is only 22%, meaning that there's a large chunk of patients who have to go through all this chemotherapy, getting all the side effects, but only to find out that there's only a very low percentage of the patient who get total response after this long phase period of time. So is there a way that we could provide non-invasive image-guided therapy assessment so that part of the patient may not have to go through this entire process? So this is the initial study that we started, that we scan MR fingerprinting at the baseline of those patients before chemotherapy, and then right after the first cycle, and then at the end after the fourth cycle, we can have some numbers across the treatment process. The goal is to see that, okay, whether we could use the change of the value to predict the treatment response. So this is some initial very promising results, meaning that right after the first cycle, we can use the difference of T1 and T2 relaxation time to separate out non-responders and responders. Of course, this non-responder, so of course the responder can be partial response or total response, but at least we can piece out, we can identify those patients who have no response at all and change the treatment strategy at the beginning rather than letting them go through the entire process. So here, maybe we can use the delta T1 and delta T2 as a marker for treatment response monitoring. So another case I want to show you is the baby study. My institute is part of the consortium that studied the outcome of babies with opioid exposure. So basically, we try to see those babies who have prenatal opioid exposure, how's their developmental trajectory would look like. So this is purely non-invasive. We want to use imaging to estimate this. But for those babies who have prenatal opioid exposure, one unique thing you will find out is that those babies are very fuzzy. It's very challenging for them to fall asleep because they have withdrawal symptoms once they're born. It's very tough scan at the beginning because now the clinical MR cannot generate good quality of images at all. So this is one example of the 10 days old baby who clearly couldn't fall asleep fully. Even though we reduced the MR scan time to just 2 minutes or 3 minutes, we can see lots of motion artifacts from a series of scans. So this is MR T2 weighted, MRI T1 weighted, and because the artifacts is just too bad, we repeated the MRI T1 weighted scan again, still not addressing anything, because once the baby is awake, there's no way that you can ask the babies to keep still. So this is the same subject who had this MR fingerprinting scan. And after the scan, we synthesized the clinical weighted images and directly compare the image quality with the clinical MR now. So there's no motion artifacts at all. And sorry. Do you see my? Sorry. Okay. Yeah. So there's no motion artifacts. Once this motion artifacts is removed, we can now start to see the early developmental sign in the deep nuclei. It's more of a myelination sign, very early myelination sign. And the cortical structures become very clear as compared to this. So at the beginning, we already provide much better image quality as compared to the clinical MR. And as I mentioned, now we also provide quantitative values. And the good thing for quantitative values is that we can track longitudinally now. So this is the research from my colleague who's using MR fingerprinting to track the developmental, to study the developmental on the healthy babies, not oval here, from 6 months to 52 months. So from each MR fingerprinting scan, there's a result. There are T1 map, T2 map, and the myelin water fraction map from the same scan. So all these are quantitative. So the myelin water fraction map is the additional image we can generate from the MR fingerprinting scan without additional scan time. So basically it quantifies what's the myelin fraction in there. So you can clearly see that at the 6 months, there's not much myelin development of the whole brain. But as the age increase, you can see the gradual increase of the myelin distribution across the entire brain, and also the fraction becomes much higher, meaning that there's this baby, those babies went through the developmental. There's a significant developmental changes in the brain. And I want to emphasize that it's not just, sorry, my mouse can be very sensitive. I want to emphasize that the size is, of course, one thing. You can clearly see that the brain size increases, but more importantly, the tissue also changes across as a function of age. That the tissue changes, we can only measure it from the quantitative tissue maps rather than weighted MR. So here, by using the quantitative tissue property maps, we can actually plot, we can actually plot the developmental trajectory as a function of age using different quantitative values, right? And different colors represent the values from different parts of the brain. So all these are not available from weighted MR. In addition to quantitative markers, I want to also talk about the reproducibility studies, which is also quite important and interesting. So by collaborating with Siemens, we started to evaluate the reproducibility and the repeatability of those quantitative maps derived from MR fingerprinting scan. So this is one study published in Radiology, 10 healthy volunteers, 10 scanners, different models, 4 sites. Repeatability of those T1, T2 values. For T1 is 3%, T2 less than 8%. So, which is pretty low as compared to conventional quantitative method, and also very low as compared to clinical MR, which I'm going to show you later. But also, here we can see that the repeatability and the reproducibility are at the same level, which is also good, meaning that even across different sites, we can get similar amount of measurement variations. So this is the comparison between reproducibility between MR fingerprinting T1, T2 maps and the clinical MR that includes T1 weighted MP-RAGE, T2 weighted, and FLAIR. Those 3 are the most commonly used clinical scans. The ICC, basically intra-class correlation, is a measure of reproducibility. Of course, the higher or the closer to the 1, meaning that higher reproducibility. And you can see the significant improvement of the reproducibility using quantitative MR technology. So what does that mean, or what's the high reproducibility will contribute to the measurements, or what we want to measure? Is that once we reduce the variation of measurements, now the actual physiological and the pathological changes can be more obvious. So so in certain ways, we try to improve the sensitivity and the specificity of detecting what we actually want to measure. That may include physiological variation of the whole brain or very subtle lesions that we already seen. So here, it's more of a transformative precision idea that if we can make the first step more precise and more reproducible, those precisions can be translatable to the following image analysis and clinical decision support as well. So this is the pipeline that we currently use for brain tumor study. So from the MR fingerprinting scan, the benefit is truly the quantitative values and the high reproducibility. And following that, we start to evaluate the image features. So this is one example. We derive the radiomics features from those MR fingerprinting maps and MR images. So this is GLCM is one of those image features, and we estimate the reproducibility of this GLCM features between MR fingerprinting and MRI. This plot basically showing that what's the fraction of those features have the high or excellent reproducibility, which means that ICC larger than 0.9. So we can clearly see that 52% of the MR fingerprinting features have the excellent reproducibility versus only 9% from MRI-derived features. So again, it's more of a transformative precision that once we have the better quality control of the first step, and that will contribute to better reproducible image features or even other AI features in the downstream analysis. And then we use the entire pipeline to detect a very subtle brain tumor infiltration area. So this is the one case that for GBM, glioblastoma patients, their brain tumor is it's very easy to detect, but what caused the brain tumor to recur or tumor recurrence is the infiltration area right next to the brain tumor, per-tumor region. So whether we can predict the infiltration of those brain tumor in the per-tumor region is very important for image-guided surgery and treatment. So we form an academic industry partnership for clinical translation that starting from the MR, the better image generation side, MR fingerprinting, to the image analysis and AI, we partnered with University Hospital Cleveland Medical Center for clinical validation. The goal is to really put the quantitative MR scans and analysis into the clinical workflow, and then partner with Siemens for the commercialization. So we hope that everything will be in the clinical workflow so that there's no gap between the research protocol and the clinical decision. So that's basically the history of what I work in the lab, where we can just work on the computer using MATLAB to look at images to after a few years, we deliver the quantitative maps to the reading room, to the clinical PAC system. And recently, we sent the MR fingerprinting maps and the brain tumor infiltration map to the OR so that we can really estimate what's the benefit of using image for image-guided treatment. So this is one example that we basically formed from the image side, we use all the images to predict brain tumor infiltration risk. And from the validation side, we collaborate with neurosurgeon to have biopsies, and so that we can have some a validation point to further improve our prediction. So this is one example that the biopsy were performed on 3 sites. 2 are positive and 1 are negative, which actually corresponding to our prediction infiltration maps. One last thing that I want to show is that, of course, we keep trying to improve our imaging technology so that we can have more sensitive image markers. But again, the question goes to why, how do we tell? So let's say if I can detect a lesion that causes seizure, what's the mechanism? What's the tissue baseline? So we also through the collaboration with Cardiff University in the UK, we're trying to connect the dots and say one thing is improve the imaging, and another thing is really to find the connection between tissue pathology, histopathology, and the image, and using tissue modeling to connect this to two scales. So this is still an ongoing work. Hopefully, we will identify what's the actual tissue histopathology source of those very subtle epilepsy lesion. Also, I guess that this 5-minute scan has been implemented to many different places, including the University Hospital Cleveland Medical Center. We've been using this for routine brain tumor protocol, have been extended to prostate, liver, and breast scan. Cleveland Clinic has started to use this as a research epilepsy protocol and Alzheimer's disease center protocol. We also ship the scans to other parts of the world. Of course, through collaborations with Siemens, this can be really globally distributed. Yeah, FDA cleared in early 2023, so hopefully we'll see the product scan very soon. So yeah, so that's all my talk. Hopefully I showed all the aspects of the quantitative MR. So this is the overview side. That was what we really want to achieve. That will be all.
Fantastic. Thank you very much. Very fascinating talk. We have time for questions. So as usual, if you have a question for Dr. Ma, please either unmute yourself and ask it out loud, or if you type a question into the chat, I will read it out loud. So we have questions from the room at the Glen. Please go ahead.
Hello, everyone. Thank you very much for the amazing presentation. I had a couple of questions, and I was wondering, I would like to know your opinion regarding which have been the biggest obstacles that MRF have faced, and maybe have stopped a faster adoption of MRF in a clinical setting and in the MRI community in itself.
So a biggest obstacle, I guess, for translation-wise, I think MR fingerprinting scan is still it's not a routine scan. So it takes a long time for people to implement this and validate this. And in terms of reconstruction, typical reconstruction is long. So we're also trying to really accelerate the reconstruction. So after the scan, it won't be hours to get the images. That's also very critical for clinical translation. One thing is fast scan. The other is the very fast turnout time that you see the maps. So that's the on the technical side. On the clinical side, another key question for clinicians to start using this is to see what's the added value. Of course, I show some epilepsy cases, and we start to show more of a brain tumor cases. But what's the killer application that really convinces the clinicians to say, okay, I want to use this scan for all my patients? This is also a challenging thing, and I really think it may take some time to really build up the clinical evidence to show quantitative MR is a clinically need or high need from clinical side, because adding additional even 5 minutes needs some justification as well. Not to mention, adding 5 minutes for all the patients. So that's on the clinical translation side.
That is really interesting. And I wonder, maybe a second question is, how has your group adopted new technologies, mainly linked to AI, towards the construction of dictionaries and the reduction of computational resources when it comes to calculate those dictionaries and to do dictionary matching and all those steps during the MRF pipeline?
Well, AI can be implemented into every component of this workflow. So from the dictionary, as you mentioned, yes, other groups have already used AI or to do the matching. So there's no need to compute a giant dictionary. So that's one side. Also, as I mentioned, once you generate maps, how do you do the image analysis or prediction? There are lots of opportunities for AI as well.
Thank you so much.
Cool. All right, Mirta, you had your question.
Yeah. Thank you so much. This was really interesting. So my question was about the reproducibility rates, and maybe I am not understanding that correctly, but all of these were below 10%. Is this the amount by which the reproducibility rate is quantified, or the deviation is quantified? If so, and then how does that depend on the strength of the field, or is there any? Yeah.
So the 3% and 8% is deviation. It's more of a variance.
Okay.
Remember, the paper estimate the deviation across the main tissue, for example, white matter and gray matter, across different side scans and subjects. So that study was performed on 3T. Not sure. So I remember there was another study published of estimating the reproducibility on 1.5T. So yeah. So I guess people have been doing reproducibility in different fields, mainly on 3T or 1.5T.
Thank you.
Super. And Eugene, you're next.
Thank you very much, Dr. Ma, for your question. For your presentation. I have a question regarding the slide where you presented for combining histopathology images to give insights for the MR as well. I saw the paper that you references date back to a decade ago, but it's, I just Googled a little bit. It's quite a popular one. I wonder if there's any more recent work that you're involved with that sort of combine the two spatial scale modalities together that could provide insights from micro scale to more of a millimeter scale, centimeter scale.
Yeah, this study is still ongoing work.
Okay.
So there's no new publication relating to MR fingerprinting findings with the pathology. This is really the thing we still are addressing right now. Yeah.
what are some of the main challenges, or I guess what's the most crucial thing that you're looking for in the histopathology? For example, are you retrieving retrospective slides, or how do you know something is going to match? Whether, the diagnostic slides that you have may not be from a specific tumor section that could be corresponding to the MR image. So how do you make sure that, or is this even a question to be made sure of? Is it even worth it to go that direction? I'm just curious about how you feel about all of this questions.
Oh, so this is a multi-center collaboration. First of all, my role is on the imaging
Okay.
side. We plan to do prospective patient scan and and operation as well.
Okay, so you're gonna try to make sure whatever you're imaging on the MR is matching with whatever you're getting from the histopathology scale?
Yeah. So
okay.
it also depends on what you want to see from both sides, right? So from the imaging side, of course, we can quantify T1, T2, but also we want to identify some tissue microstructure related features that directly relate to what you can see from the tissue side. For example, cell size, enlarged balloon cells. So there are some features we want to coordinate. It's not just intensity, because from the tissue side you can get some microstructure features. Then we try to, from the image side, we're trying to match those features using special design. So this is one on the feature correlation. Of course, there are lots of other challenges, including the tissue image alignments and other things. Yeah, I'm sure this is a very challenging process.
Cool. Thank you very much. I'll be looking forward to seeing this work coming out. Thanks.
Excellent. Other questions? I thought of one earlier on. I guess I'll ask. The time. So you showed the example or the study of the pediatric opioid study, and the motion artifacts were not present at all with the fingerprinting technique, but I was thinking your scan times are similar, right? We're still on the order of minutes. So how do you eliminate that?
So two ways. One is that MR fingerprinting has this inherent error tolerance because it's a matching. So the example I want to make is always back to the human fingerprints. Because lots of times the human fingerprints are retrieved from the crime scene when there's just a partial fingerprints, but using the matching technology, you can still find the right person. It's similarly for MR fingerprinting scan as well. So because you have a big dictionary and the matching process, and you have a very high error tolerance for what the quality of the signals you acquire. So this is the one thing. Another thing is that we also prospectively on the sequence side design this motion detection and correction technology. So basically, during the MR fingerprinting scan, we can detect the motion or monitor the motion and use those motion information to correct for the case space. And then so that the resulting data will be less affected by the motion. So there are two ways.
So beyond just quantitative MR data, you're also able to do artifact correction, correct?
Yeah, motion correction.
Just motion?
Other artifacts as well, I guess, because the reason why we can make the MR fingerprinting so fast is that we applied a very high undersampling rate. So the results of the undersampling is just that there's many aliasing artifacts in the images. So through the template matching, we can get rid of this aliasing artifacts as well. So that means, so I guess in terms of artifacts, that can be from motion, can be from aliasing artifacts or thermal noise measurement errors as well.
Okay, very nice. Any other questions? If not, I'd like to thank our speaker again and thank you all for attending today. This was wonderful. and have a great weekend. Thank you.
Thank you. Thank you.
Thank
Bye.
you. Thank you for being here. Bye-bye.